All right, so we're going to kind of touch on some of the biggest issues with Kubernetes cost management and kind of some of the ways to combat it. We do have quite a bit of data on this, so hopefully I'll be able to talk through that. I am going to attempt to talk relatively fast so that people have time to ask questions, because it's a lot better with a back and forth. And I have my little thing so I can walk around. So let's go ahead and get started. So we did a review last year of about 4,000 clusters that connected to Cast AI. We analyzed kind of what the resource utilization looked like across all those 4,000 clusters. That spanned Azure, AWS, GCP, big clusters, small clusters, kind of running the gamut. And so we're going to go over some of that data and then how to actually fix those issues. Hopefully, if anybody is running Kubernetes out there, this will make you feel a little bit better about yourselves, because it's an industry-wide problem. It's not just you. So this is some of the stuff that we analyzed. I'll go past that one. 13% of what people are paying for in Kubernetes for compute is actually being used. 13% of the actual CPU cycles that people pay for are being consumed by the applications that are running on Kubernetes. Abysmal, awful, terrible. If you did this in any other sector of your business, you'd be fired. But when it's in cloud, people are like, it's hard to measure, it's hard to fix, we don't want to worry about it. We see this all the time. And this is industry-wide across different verticals, across different industries. Even really well-optimized customers, when they come to us, are in the 16, 17% range, maybe 18%. It's really, really bad. And a lot of that's driven out of fear, and we'll touch on that a little bit later. Memory is only slightly better at 20%. And that's because memory is a lot more static, right? There's a lot of Java workloads out there. The heap is how much you need. It's very easy to set your requests and limits around memory. Java or Golang, Python are sometimes a little wonky. There's some ways to kind of fix that, but memory is typically a little bit more predictable. CPU is super spiky, and as a result, people tend to over-provision it a lot because they're afraid of what's going to happen if they under-provision it. And a lot of times, people aren't using HPAs very effectively either. The gap between provisioned and requested is growing. So the waste in clusters is getting larger. We've done this report 2 years in a row, year over year, and it's getting worse. And I think a lot of that is more people are migrating to Kubernetes, especially more large enterprises are migrating to Kubernetes. And a lot of people, the way that they've done Kubernetes is they Google, how do I install Kubernetes? And they grab a deployment file, and somebody out there who is really interested in learning Kubernetes and wants to put it on their resume will create a deployment file. They'll create their application. They'll be the first application launched in their Kubernetes cluster at their company, and they're very proud of themselves. And then 500 other engineers will copy pasta that deployment file with 0 changes except the image and the environment variables and maybe a couple of other tweaks. And so now you've got the same requests and limits set across 200 different workloads with some maybe minor adjustments because something tipped over and they said, oh, I need more memory, which is typically why things tip over is memory. Like, things don't tip over because of CPU. It's always memory. All right, some of the top culprits. Ridiculous over-provisioning, right? That could be wrong instance type selection. Again, people set up Kubernetes cluster 2 or 3 years ago. They set up a node group. They said, yep, we're going to use M5A 4x larges because that fits our Java workload really well. I can pack 6 pods to an M5A 4 extra large. It's great. They set up auto-scaling on it. They're doing great. And now they've got Java applications, Golang applications, Python applications, Node.js for some reason. All across the board, right? So now all these different applications have different sizes, different shapes, different needs, and they're all still running on those M5A 4 extra larges. So now you've got some nodes that are running pegged on CPU and 20% on memory because they got stacked with a bunch of Golang workloads. You've got other nodes that are running pegged on memory because all the Java workloads landed on them and they're using 20% of their CPU. Not a good fit, right? This is sort of a culprit of the whole shift left mentality, right? Everything is code, infrastructure is code, Terraform, yada, yada, yada. We'll touch on that a little bit later. The other one is actually requests and limits around workloads. Sometimes it's accidentally over-provisioning. Sometimes it's on purpose over-provisioning because people don't want to get woken up at 2 o'clock in the morning because something tipped over. So they say, well, I'm going to give it half a core and 2 gigs of memory because that's what it used on my laptop. Well, most people don't actually performance test. And the other issue is that people run the same settings in dev, staging, QA, pre-prod, whatever else, integration, whatever other environments you have, UAT, whatever else you want to call it, that are exactly the same as prod. Your dev environment likely has almost 0 utilization. It is there so that when somebody merges code and deploys it into their environment, They can make sure all the wiring worked, all the smoke tests worked, all the canaries worked, and the utilization is like that. A couple weeks ago, we saved a customer 96% on their dev environment. $25,000 a month down to $1,500 a month on their dev environment. It was that far over provisioned. From both a node over provisioning, resource request over provisioning. They moved a little bit of it to spot instances because spot instances are great in your dev and your pre-prod environments. So there's a lot of ways that you can combat that. Unwarranted headroom, this is kind of what we talked about with requests being set too high. And also, I mean, people do this on nodes too. I've seen people provision an M5 or an M6 or an R5 or an R6, and they'll have the CPU pegged and the memory will be at 40%. I'll ask them, well, why didn't you go with an M5 or a C5 instead of the bigger instance? Oh, well, we need more memory. We burst on memory, and we get kills if we use those smaller instances. Well, then request more memory. You're already paying for it. Having requests and limits not equal on memory, you still have to pay for the memory because you're going to kill if you don't anyways. So you're just paying for it in a different spot. You might as well request what you actually need and set your requests and limits equal and have those boxes be full because you're already paying for the memory anyways on those boxes. You know, those M5s that you're showing 40% utilization on memory, it's actually using more of that anyways because you're planning for those bursting. So you might as well allocate it correctly to the pods. Now you're not going to have to worry about kills and you can bin pack appropriately. You can actually pack around those correctly. The last thing is pricing arbitrage. This is what I touched on with spot instances a little bit. Spot instances are incredibly powerful if used properly. One of the worst things you can do with spot instances is take the existing on-demand instance that you've been using for the past 3 years and say, I'm going to buy those in spot now. Why? Because you were using it before? Like right now, I'll tell you a quick anecdote. The G6 instance type on AWS is the cheapest instance type on AWS worldwide. For those of you who don't know, a G6 is 5th gen Intel Xeon, latest generation Intel Xeon processor, and it's running an L4 NVIDIA graphics card. It's like a $50,000 graphics card, the most advanced NVIDIA graphics card that AWS offers. These instances are ridiculously expensive on demand. They are the cheapest instance you can buy on the spot marketplace. Nobody would provision that intuitively as a spot instance just by guessing, right? They launched about a month ago. The thing is, AWS built out a tremendous amount of capacity to plan for when people start migrating to these. People haven't migrated to them yet. As people start using those, the spot prices will start going up. But for 1 month, 2 months, 4 months, 5 months, 6 months, you'll get really great pricing on fantastic machines, really strong, powerful machines. We've seen similar things happen in GCP. Last year, GCP launched the C3 instance type. Again, it was the 4th gen Intel Xeons, really powerful general purpose compute instances. They launched them at 0.4 cents per CPU hour. It was the least expensive instance in the world on any cloud provider on the spot market. And I'm going to toot our own horn a little bit here. I try not to be too salesy in this, but we automatically rotated those into one of our customers' clusters. They had 200,000 CPUs globally. We put, I don't know, something like 50, 60,000 CPUs worth of C3s into those clusters. They saved $250,000 in the first month. That pricing lasted 6 months. That customer saved $1.5 million last year with no effort. They didn't do anything. It automatically arbitraged in and lowered the spot price on those clusters by about 33% of what they were using, 33 to 40% on the nodes that were moved over to C3. They basically drained down the entire C3 capacity in every region they were in by using them like that. They saved $1.5 million in a complete windfall. The company didn't expect it. They were able to reuse that money on other projects. They were able to advance further things. Fantastic use of spot instances. That's one thing when you're using spot instances appropriately and you're arbitraging automation across those, tremendous savings. And this is the big key, right? Automation. Automation in your environments to be able to select instance types, to be able to right size your workloads, to be able to bin pack, all of those things being done automatically cannot be done by hand. It's not a manual process. And whether you're using an open source tool that does it, there's several out there. There's several companies out there that do it. I mean, we're obviously one of them. That's why we know the space pretty well. Doing automation pays for itself in dividends by far, right? And being open-minded to the instance types. We see a lot of people who are like, oh, well, we only performance tested on M5s. Well, M5s are a 3-year-old instance. I guarantee the M6s are going to give you equal or better performance. R6s are going to give you better performance. Everything newer is going to give you better performance. So to lock into a 3-year-old instance type, because that's what we've always done, is a really bad practice. We've actually seen customers that had RIs, bought a tremendous amount of RIs, 3-year RI on M4s. They were paying more for their reserved M4s than they could have bought a modern generation M6 at the same time. That would have been significantly faster, about 30 to 40% faster. And they were paying more for their old ones, but they were locked into them. They had to pay them. And this is where going with like compute savings plans instead of RIs is much more beneficial, because then you can switch around types. If you have to do on demand, we have a lot of people that have Java Spring Boot applications that can't run on Spot. They take 10 minutes to boot up. I'm sure I see smiles in the crowd. There's a lot of people running that stuff. Do savings plans. AWS has changed the pricing model between RIs and savings plans. They're almost the same on discounting now. The CSPs are within, I think it's 2 to 4%, something like that, of RIs. You're better off just going with CSPs and locking in the flexibility, and only do the bare minimum. You don't want to do 100% coverage on a CSP or an RI or anything like that, because 6 months from now, when your team says, oh, hey, we found a really good way to save some money, we were able to reduce the footprint, or we changed this algorithm to move a lot faster, or we moved Kafka into managed service because it was dying on our cluster, and now you need 20% less CPUs across your clusters, well, you're locked in, right? You're stuck on that. Buy your baseline capacity in a CSP, and then use spot instances to burst if you can, or just pay on-demand prices for the other ones. Or do a longer-term CSP on your base capacity, some minimal, 40, 50% of your capacity, like a 3-year, and then do smaller incremental, like quarterly 1-year buys on your additional capacity. So that way you're phasing out CSPs every quarter and you're letting them drop off. Like, these are some of the big issues that we've come across with some of our customers, where they bought in at 100% capacity. 2 or 3 months later, their engineers said, hey, we found this great tool. It compressed all our environments. It's going to reduce our spend a lot. Well, the FinOps guy said, well, I already bought RIs and CSPs to cover all of our on-demand. They said, but we're switching to spot instances, and we reduced our CPU usage by 20%. He said, well, we still got to pay for it. I mean, we've actually seen a FinOps person get fired over that. Like, he locked in the company, and this was a company that was struggling. This was 2 years ago. It was a company that was struggling financially. He locked them into such a large, it was actually CUDs on GCP, such a large CUD purchase on GCP that the company was struggling to be able to make the payments. They didn't need anywhere near that. They cut their CPU usage by 60%, and the FinOps team came in and said, hey, look, we're still paying for it. You're actually costing us more because you moved things to Spot, and now we've got to pay for those Spot instances and the RIs that we bought and the CUDs that we bought. I mean, it's heartbreaking, absolutely heartbreaking, especially for a financially insolvent company, as a company that was struggling financially. And they were having a lot of problems. They had to do layoffs, they had to do other restructuring, like they had to raise a down round. Like, it's a tough market out there, and those kind of mistakes can be very, very costly. So automation, key. Making smart choices, key. Shifting things right. So we've been talking about shifting left for the past 10 or so years, right? Everything has to be code. Security is code, infrastructure is code, testing is code, everything is code. Automation in this area should be done at runtime. Set guardrails in your code, right? Set baselines in your code, but then let the automation take care of it at runtime. You don't set a static number of nodes in your Terraform. You set a node group, and then you let the node group auto-scale based on what the requirements are. Why would you do things differently across any other space? Your node selection criteria, put some guardrails around it, choose the best cost instance. No reason to lock in your instance type to a single instance type or a small number of instance types. Arbitrage across everything that's out there that's going to meet your performance needs. Most of the instance types that are available in the cloud have negligible performance differences on 99% of applications. Most any REST API, most any platform, you're going to see almost the same performance across every instance family that's, for instance, AWS. Anything that's a 5th gen and above, you're likely not running hot enough that you're going to see a performance difference across the different generations. Don't lock into a single one. Stay very broad-minded there. Using automation, deciding those things at runtime, what's the right shape, what's the right size, all of that, doing that at runtime. Same thing with your workloads. Auto-scaling your workloads both vertically and horizontally is something that's done at runtime. Like, we really need to be encouraging some of this stuff to be done at runtime. I get asked all the time, how do you guys interact with Terraform? I said, well, we don't break Terraform because we don't change the things that Terraform manages, but Terraform only sets out a framework. The actual inner workings should be done at runtime. And that's what we've been advocating for. This is an example of what true automation and what effective can have. The blue line is what they're paying for. The gold line is what they're actually using. On the left, that was using cluster autoscaler that was actually a fairly well-tuned cluster autoscaler. And if you look at how poorly the blue line tracks down, right, it scales up just fine. Cloud providers are more than happy to give you additional resources, more than happy to increase the size of your cluster. Very, very reluctant to decrease the size of your cluster. As you can see on the left, the downscaling just about hits right when the upscaling starts on the next day. So all that waste, all that gap is waste. On the right-hand side, they're paying for what they're using. That's just-in-time capacity. That's where you get real efficiencies in there. I think I have about 5 minutes left. Is it?
No,
or 10 minutes left?
10, 15 minutes.
Oh, okay, cool. We got plenty of time. Oh, I went way too fast then. All right, any questions? Go ahead.
So just now before the slide, you mentioned Terraform
Mm-hmm.
And how this integrates with Terraform. How do you shift right instance selection in Terraform?
So we don't use it. Well, Terraform aligns the policies, right? So even on our platform, and there's other tools out there similar to ours. You know, I'm most familiar with ours. So again, I apologize. I'm trying not to make this too much of a sales pitch, but I know Cast AI very well. We use Terraform to kind of set the framework, set the policies, set the guardrails, and then everything else is decided by the engine at runtime, by the automation at runtime. So you can still control policies in high level using Terraform. You don't have drift because Terraform doesn't control the nodes, right? Same thing with workload right sizing. Workload right sizing doesn't change the deployment file. It changes the pod. The pod is not the controlled piece. It's the child. It's not the parent. As long as you're not changing the parent, you don't have sync issues with things like Argo CD and Flux CD. So you don't end up with conflicts with like your GitOps, your traditional GitOps. You can backport requests and limits back into your GitOps pipeline if you choose to. I would argue that it's actually not necessary and it's kind of a waste of time and effort. Set your baseline, do your best estimate, do your guesses on your requests and limits, but then allow the automation to actually do the fine tuning out in production in real time to adjust based on your market conditions. Go ahead, Raymond.
You mentioned having guaranteed requests for memory,
Mm-hmm.
keeping the memory and limits the same. Are you seeing other customers remove the CPU limits at all, or is that like a recommendation?
So we remove CPU limits in our automation. We're seeing a lot of customers removing CPU limits in general. Generally speaking, you're good to remove CPU limits. Set your requests at something like a P90, P95, somewhere in that range, and then allow bursting above without limits. The only kind of gotcha to that is if you have workloads that, for instance, I've seen some Java Spring Boot applications where at boot up time, they are absolute monsters with the JVM boot up and the application boot up. They can cripple some of your other application and increase latency and cause CPU starvation on other apps. That's the only case, or especially if you've got many, many, many Java applications all starting up at the same time and they're all trying to in-rush, you can actually cripple the kubelet. I've actually seen people crash nodes because the kubelet can't get enough CPU cycle to heartbeat back to the control plane, and the kubelet will actually go unavailable. Those are cases, edge cases, where setting a somewhat modest limit on CPU makes sense. But those are relative edge cases. I don't see that very often. 1 out of every 20 customers, maybe, if that. So generally, removing CPU limits is not an issue. Anybody else? I have more stuff I can talk to. All right, go ahead. Good question. So I actually advocate for segregating stateful stuff, and I'm a opponent of node groups in general. Node groups are sort of an antiquated technology. They're no longer necessary with the tools Kubernetes offers. However, for things like stateful sets, I do encourage people to segregate off your stateful sets into node group, node pool. We call them node templates, which are more logical groupings than hard groupings like node groups are. Put your stateful stuff, basically stick it in a corner, tell it to leave everybody else alone, and stick it there, optimize it once, because it's not going to be auto-scaling. It's, if you've got an Elk stack or if you've got Kafka, Redis, things like that, they're typically not auto-scaling. Stick them in a corner, pick the right size nodes for them one time, do automation on them one time, get them lined up, put all your stateless stuff together. The worst thing you can have happen is to have one Kafka pod or one Redis pod or one MongoDB pod or whatever your stateful sets are spread across every node in your cluster. If you've got 50 or 60 nodes in your cluster and there's one stateful set on every single node, now that whole cluster is locked. You can't bin pack, you can't compress, because typically most applications don't want to move stateful sets because there's no idea whether it's going to crash things, whether it's going to break things. So you can't bin pack very well if you've got stateful sets kind of scattershot throughout your cluster. So that's one instance where using node segregation of workloads, stick your stateful stuff together, stick your stateless stuff together. If you've got maybe like GPU workloads, stick those together. Those are 3 technical use cases where segregating workloads makes sense. Otherwise, workloads should entirely be integrated. People intuitively think, I want to put my memory-heavy workloads on memory-heavy nodes. I'm going to put my CPU-heavy workloads on CPU-heavy nodes. That's actually counter to getting good optimization. Because if you've got a CPU-heavy workload, you stick it on a node that has a memory-heavy workload, they actually complement each other, right? One of them's using more of the CPU, the other one's stacked up heavy on the memory, and you get much, much better bin packing and much better resource utilization by mixing all those workloads together and letting them kind of arrange each other around each other.
What about long-lived, like a web server, and something bursty, like a fast job?
Sure. I have seen cases where it makes sense to segregate those. It depends on kind of what your architecture looks like and how big the different pods are. Sometimes it does make sense to kind of put your batch jobs off to the side because you don't want them scaling up and then having one long-lived one on each side. It depends on if your long-lived ones can't be bin packed, right? And at that point, they're stateful, right? And they should be grouped in with stateful stuff. Like if you've got a Java Spring Boot where you can't move it, right? It takes 10 minutes to start up. It doesn't auto scale horizontally very well. I would count that as stateful, right? So you group it in with your stateful stuff. Anything that has like a really long startup time. One thing that I didn't mention in here that I did mention in the talk I did last night is your Kubernetes configuration matters, right? Using the right configuration for the right job. Pod anti-affinity. Great if you've got 2 pods. Fantastic, great. It's going to guarantee your 2 pods are on separate nodes. Good. Pod anti-affinity, awful if you have 50 pods. You're going to have 50 nodes. A lot of them are going to have 1 pod on them. And a lot of times that's going to be a 250 millicore pod on a 2-core node. You just wasted a core and a half once you figure, well, a core and 3/4 when you factor in the overhead and everything else, right? Use something like topology spread constraints. Topology spread constraints tends to scale a lot better. You can have, if you use topology spread on availability zone, you're going to get separation across the availability zones. They're going to naturally spread out across different nodes as they're scaling up and down, and you're going to get good enough distribution. Obviously plan for, when you have a really resilient architecture, you are going to have a little bit of wasted applications. You might only need 8 replicas to run your service, but maybe you're running 10. Those extra 2 are extra resiliency. But if you're that resilient, you can run them on spot. So now you're running an 80% discount on the instances. You can eat an extra 2 replicas to make sure you have the resiliency that you need, right? Especially if you're running something like Golang, which has a super fast startup time. If you're using a tool that's actually managing the spot instances intelligently, it can intercept the spot interruption notice. So AWS gives it 2 minutes, GCP is 30 seconds, Azure I think is 30 seconds. You can intercept those and start spinning up a new node immediately. In AWS, you can actually beat that 2-minute warning. You'll have replacement capacity before the node gets taken away. And then you're just moving your pods over and starting them back up again. GCP and Azure, you're going to have a small downtime, right? So that's where using topology spread, making sure your workloads are set up, and having a couple of extra replicas out there, having your HPA set up to have a little bit of extra capacity. If you lose 1 or 2 replicas for 30 seconds, you're still going to have enough capacity to hit your demands. Any other questions? We still got a few minutes left. Go ahead.
So in the case where you have like a Java Spring Boot application that you mentioned and it requires a long startup time, if you throw like more CPU at it initially, it will start quicker. With the new Kubernetes like dynamic resource allocation, is it then possible to have like
Yes.
more CPU when it starts up and then lower it later?
Yes. So 1.30, for those of you who don't know, in 1.30, Kubernetes launched in-place right-sizing. You can change requests and limits without having to restart the pod. This is going to be a game changer for right-sizing your architecture on the fly. We're adding support for it this month, I think. I don't know that AWS has actually launched 1.30 into stable yet. I think it should be out within a week or two. GCP, I think, has it in rapid. I don't know if they've gone to stable yet. It's any day now. But that's going to be a game changer on getting your workloads to the right size, because then you can burst them on startup. You can give it a core as default, and then you can have your automated right sizing 45, 50 seconds, a minute, 2 minutes in, correct it back down, and then you can pack other pods around it. That's going to be a huge game changer, especially for those big applications like Java that have a huge inrush. I wish I had put my longer slide deck on here. I didn't have enough stuff to talk about. I was worried about running out of time. Anybody else have other questions? Oh, I guess one thing I can mention too. Go ahead.
How popular is Carpenter?
Carpenter's pretty popular. So it's a semi-competitor of ours. It does similar things from a node provisioning perspective of what Cast AI does. It's a good platform.
Does it do the shift right on instance selection?
It does. It requires a lot more hand-holding. It's like any other open source tool, right? It's going to require a lot more tinkering. I've seen customers that spent 6 months really dialing in, tuning in the settings, dialing in the times on it, dialing in the instance types and stuff, and they've achieved extremely high rates of efficiency across their cluster. It's not going to impact workloads. It's only going to impact the node selection. So their request to provisioned was really tight. But it doesn't help you with the request to used number. But it's still a lot better than cluster autoscaler for sure, 100%. But it requires a lot of tinkering. I've also seen Carpenter provision a $20,000 a month node into a cluster that was used for exactly 1 hour, and it left it sitting there for 18 days. It wasn't until we reached out to the customer and said, hey, you got this really, really expensive bare metal node running in your cluster that has been empty for a while. And he said, oh, thanks. And he went and deleted it. So like any other open source project, you really need to monitor it. You really need to dial it in. You really need to tune it. But it's far better than cluster autoscaler for sure. Typically, and I'm going to toot our own horn real quick here. We're typically about 30% more savings than Carpenter, but Carpenter's typically 30% better than cluster autoscaler. So it depends on what your goals are, what your needs are. If you have more time than money, Carpenter. If you want something that's easy out of the box, a managed solution might be a little bit easier. But yeah, Carpenter is certainly a step in the right direction. It's a lot better.
Are you seeing like a large shift to ARM-based processing?
We did see like a big burst in it last year. Like AWS specifically was really hammering on Graviton last year. And we had a lot of people being like, yeah, we're going to move to Graviton. And now this year, I'm seeing almost no additional adoption from those people who said that last year. Like, they went out and tested it. And the savings over moving to Graviton is meh. It's about 10%. There's just not a lot of bang for the buck to go rebuild all of your containers to be multi-arc. In a perfect world, if you're writing things from scratch and you're starting new, if you've got a Golang app or even Java apps or something, and you can build your Docker containers multi-arc from day one, where they can run on either ARM or x86, great. They're slightly larger containers. I forget, it's like 10 or 15% larger container images, but relatively negligible in the overall scheme of things. Then you can arbitrage between ARM and x86, especially if you're using Spot, right? Sometimes Spot is cheaper on x86, sometimes it's cheaper on ARM. So having your options there is definitely a good thing. But I'm not seeing the huge wholesale mass migration to ARM that I think AWS wishes was happening. We are seeing it in pockets here and there, but not a massive adoption. Some customers, some of our startups, cloud native startups, are building everything Graviton right from the beginning. Great, awesome. But like right now, those G6 instances that I mentioned, those are x86. Those are cheaper than anything you can buy for ARM, hands down, on the spot marketplace. Hands down. You have way better pricing on those. So if you built everything on ARM, exclusively for ARM, you're missing the boat on being able to arbitrage across 520 different x86 instance types, and you've cornered yourself into about 140 ARM instance types. So it does definitely corner you into a much smaller pool of instances on the ARM side of things. Yes? 5 minutes. Oh, now we got 5 minutes. Okay. Any other questions? I like the Q&A part better anyway. So. One other thing that impacts auto-scaling a lot that's helpful, pod disruption budgets. So I would say probably 20 to 30% of the people I work with are actually using pod disruption budgets effectively. For those of you who don't know, pod disruption budgets are incredibly important, especially if you're trying to do automation, because it's going to limit the blast radius of any type of change within your cluster. If you've got 10 pods, a pod disruption budget, you can set it to say max unavailable is 1, which means you're always going to have 9 out of 10 of your pods running. And to the point earlier about making sure you've got a slightly extra capacity in there, now you've got 90% capacity instead of 100, but you're designed to be able to run on 80%. So you're still good. You still get that extra 10% buffer. What that's going to do is when you have a node that's underutilized and it goes to drain and compress the cluster down, if you've got 3 of those pods, 3 replicas of that same workload running on that node, it's not going to nuke all 3 of those at the same time. It's going to move 1 to the new node, wait for it to start, then it's going to move the second one, then it's going to move the third one. That's going to allow you to be able to use things like spot instances or even just general bin packing and automation a lot more effectively without suffering any downtime on your applications. The downside of pod disruption budgets. If you've got a team that just copy-pasted their pod disruption budget across 250 different workloads, and some of them have 2 replicas, and some of them have 20 or 50 replicas, the same settings don't work for 2 replicas as 20 replicas. And the reason for that is a lot of people set percentages. Oh, max unavailable, 20%. Well, what's 20% of 2? If I move 1 pod, it's 50%. I'm breaking that rule. I can't move a single pod. I've got 2 replicas. They completely lock the 2 nodes that those are on. I can't drain them. Kubernetes will not allow them to drain. The pods will not move. Now you've just locked 2 nodes. Doesn't matter how underutilized they are, those 2 nodes won't move. They won't drain. That's where having people have good hygiene on their deployment files and on their settings in Kubernetes is really important, because a lot of people do just kind of copy and paste the same settings from deployment to deployment to deployment and don't actually look at what they're using. Having correct pod disruption budgets set, if you've got 2 and it's just there for resiliency, not for capacity reasons, but one of them can move, great, max unavailable 1. Now I can move 1, have it set up, now I can move the other one. You're good. Now you're not locking anything. Percentages at small replica counts will kill you. I've seen clusters where they've got a whole bunch of 2 replica just for minimum capacity, resiliency, so they had resiliency there. They all had max unavailable like 20% or 10% or something like that. They had half the cluster was locked up with these little tiny pods. So like, why are we getting terrible bin packing? I'm like, because we can't drain anything. Like nothing can drain. So they went and updated those, and they saved another like 20% on that cluster by being able to get rid of the waste in there. So yeah, no, automation is great. Being able to tune your workloads, all this stuff. Thanks for coming to my TED Talk. So